Hi students, this is Dr. Jo. Today we're going to work on this problem looking at stereoisomers. So the first question says draw a pair of enantiomers with the given connectivity shown down here. Draw a pair of diastereomers with the given connectivity. So the first thing to do is to actually turn this structure into a stereoisomer, and we'll call it stereoisomer 1. Because the tetrahedrals are not shown with dashes and wedges, you're not actually showing any stereochemistry. This is a chiral carbon, this is a chiral carbon. I'm going to arbitrarily make this one a wedge. That would make the hydrogen here go back in a dash. I'm going to arbitrarily make this one a wedge, and then make the hydrogen, we put it on the other side, a dash. Okay, there are no other chiral carbons in the molecule, there are just the two. So if I want to draw the enantiomer, okay, there are two ways in which I see students go about this. So the first way you can do it, and then I should say that students go about this correctly. The first way to do it is just to invert every chiral carbon without trying to rotate the molecule. Okay, so the OH here, the hydroxide, is going to go back. You can put the hydrogen or leave it out. And then the OH here is going to go back, and again, put the hydrogen or leave it out. So if I invert every chiral center, I have drawn a stereoisomer of my stereoisomer of reference. Okay, that's a stereoisomer 1. Now, another thing I've noticed students like to do is to, is to take the original stereoisomer, okay, and then rotate it to try and draw a mirror image. You can do that too. So another, the way to go about that is pretend you have a mirror here, right? And I don't know if I'm gonna have enough room. Okay. And everything would be reflected. So in that case, the hydroxide is still gonna be on a wedge that's nearest the carbonyl, okay, because you're just pretending you're mirroring everything across that dotted line there. Okay. There we go. And actually, if you want to be very precise and accurate, you can put the wedge on that side, but it actually doesn't matter if you put it on the right or the left. What matters is that if you are mirroring your stereoisomer like this, that you keep the hydroxides forward, because here they are forward. Okay, so those two structures on the right are the exact same structure. Now you can try to visualize how you can rotate one drawing to get the other. So these are this is the enantiomer of that original stereoisomer, okay, which is question A there. Now I'm going to draw the diastereomer, or a diastereomer of stereoisomer B. And to do that, I'm going to invert one chiral center and leave the other one the same as stereoisomer 1. Okay, so I'm just going to arbitrarily leave this chiral carbon as is, and then invert the other one. So that's going to give me a diastereomer. All right, a non-superimposable non-mirror image. And I'll let you try to rotate this, maybe make a model to convince yourself that these are non-superimposable non-mirror images. So this is a diastereomer. Ooh, let me spell that correctly. Of that original stereoisomer. There is a second diastereomer of the stereoisomer 1, which is the enantiomer of this molecule here. These are all stereoisomers of one another, right? They all have the same connectivity. They just have a different three-dimensional arrangement of their chiral centers. Okay. So this is, again, a diastereomer of 1, but it's an enantiomer of that third stereoisomer we drew. So we'll call this one 2 here. 1, 2. We'll call this one 3. Right, and we'll call this one 4. So number 4 there, my stereoisomer number 4 is a diastereomer of 1, which is what I was prompted to draw. So is this stereoisomer 3. And then if I wanted to dive a little bit further, I could also ask how are the different stereoisomers related. So that's why I wrote down that note here, even though I was not asked to do that.